This is lecture number 2, and the title of this lecture is The Dawn of Science. And while in many ways I'm going to be talking about the dawn of cosmology as a science, at some level, people looking up at the stars and thinking about how the universe works on a grand scale was really a motivating factor for science in general. So I think it's fair to sort of title this lecture The Dawn of Science, because really astronomy at some level was the first science. So let me start with a little bit of an exercise. I put up a picture here of the universe. This is my picture of what the universe is like. The Earth is flat. It's surrounded by a sky that's basically a dome, and that's it. So what I'm telling you is that our world, the world that we live in, is basically a snow globe. We're in the bottom of it, and we're looking up. How many people believe that this is true? Okay, that's good. Convince me that I'm wrong. Let's go. Raise your hand. Or I'll just start calling on people. Yeah?
It doesn't explain how it can loop back if we keep going in one direction.
Okay, so have you done that? How do you know we can do that?
Science.
Okay. Because science, okay. It's always a good answer. Can anyone give me any other evidence that this is wrong? Yeah.
The ocean disappears when you look over the horizon, or like how it bends.
You're telling me the ocean bends when you look over the horizon?
Like you can't see it, like it's curved.
It looks curved to you when you look out over the ocean?
No, not really.
Uh-huh. That's a good idea. I like that. Like, this is kind of ridiculous. Like, this is eventually you're going to run out of ocean. So I actually found this picture. I thought it looked cool, and that's why I showed it. But imagine that these holes are all plugged up, and there's some kind of plug here. But I like that. This is ridiculous. You're going to run out of ocean at some point. Very good. Give me something else. Yeah?
There would be no seasons.
There would be no seasons. Why would there be no seasons?
Because it can't tilt on an axis.
Wait, you're telling me the seasons are caused by the Earth tilting on an axis? How do you know that? Science. Okay. So, I mean, I know we're using the term science jokingly here, but fundamentally, this is what science is, right? Science is providing, you have a hypothesis. This is my hypothesis. Okay, you've already stumped me once on my hypothesis. It can't be leaking water. That's not going to last. But otherwise, how do you rule out this hypothesis? How do we know the Earth isn't flat? Yeah. Okay, so we live by the ocean, and maybe you've watched a boat sail out. What does it look like when a boat sails out? Eventually disappears, but maybe it's just getting really far away, and you just can't see it anymore. Yeah. Okay, that's good. So if you've ever, for a real long time, and I'm going to believe that some of you have done this because you go to the beach. We're not too far from a beach. If you actually are just hanging out on the beach and you watch a ship sail off, you'll see the bottom of it go away first and the tippy top of it go away last. So it's almost like, imagine you were hiking with someone and you're on the top of a curved hill and you stand on top of the hill and they walk down the hill. You'd see them, the last thing you'd be able to see is their head go down below the hill. It is almost like the ocean is curving off, because if you watch something recede from you, the ship's mast will be the last thing you see. So that's evidence that the Earth at least isn't perfectly flat, that it's starting to curve off as you sail out. So maybe it is kind of rolling off. Anything else? Yeah?
During lunar eclipses, you can see the Earth is spread.
Yeah, that's right. So I have a sense that people have gone through this problem before. That's right. But if you know what a lunar eclipse is, so like when the Earth gets in between the sun and the moon and casts a shadow on the moon, the shadow the Earth casts is always round. So that also suggests It's hard to take a disk like this, and if you tilt it by any angle, it won't always cast a perfectly round circle. But if you have a ball always casts a round shadow. How about being more general? Has anyone seen anything that convinced them that the Earth isn't flat in all of your modern experiences? Has anyone ever seen a picture of the Earth from space? Right? So these days we have a lot of evidence that the Earth is round. Okay? You've seen pictures of it. Some of you probably have flown a significant way around the world if you haven't flown all the way around the world. Okay? So you probably have some pretty direct evidence that things are different as you travel around the world. And we now know as sort of an absolute fact that the Earth does not look like this. It's a sphere, more or less a sphere. This one actually is pretty easy. So fine, I'll give you that. Let's just accept the fact. I'll accept your crazy notion that the Earth is a sphere. But what's going on is this. The Earth is sitting here, and every morning the sun rises and sets. And so what's going on is the Earth is sitting still, and the sun comes up and goes over my head and then goes beneath the Earth on the other side of the Earth. And while it's on the other side of the Earth, it's dark. It's dark for me. And then when it comes back to my side, that's when it's daytime. The sun goes around the Earth once every roughly 24 hours, and that explains everything. The stars also rise up at night and then set. That's because they're also going around us. And the planets do the same thing. They're moving in slightly different circles than the other things because they moved with respect to the background stars. But otherwise, this model explains all that stuff. And it's a very natural thing. That's what it looks like, right? When I go outside, we actually say the sun rises and sets, right? The sun's moving, rises and sets. We don't say the Earth tilts to block out the sun so we can't see it anymore, right? We say the sun sets. Why is this wrong? Convince me this is wrong. You got anything? Who believes that this is wrong? Good. Okay, good. Science. Right? Okay, you got something?
It doesn't explain why this happens at different times in the world.
Why sundown and sunset happen at different times in the world?
Yeah.
Well, if the Earth is round and the sun's going around us, the shadow, the position of the shadow would change.
But the side that we're looking at wouldn't have the same, it going over their head.
I mean, this side here?
Yeah.
Well, this might be a pole, like at the North Pole, for example, this time of year, the sun never sets. Right? So you would see it all the time. So, yeah.
We could look at something like retrograde motion where
What's retrograde motion?
when the Earth's, it's going faster at one point than Mars. So when we look at Mars's orbit, it'll look like it's going backwards.
Mm-hmm. So you say something about retrograde motion. I think what you're saying is you study the sky very carefully, and over the course of several years, you've noticed that every couple years, Mars, with its path in the sky with respect to the background stars, doesn't continue in a straight line, but it backs up and goes forward again. That's called retrograde motion. We'll talk about this later in the course. So, that's true. That's true. That very specific observation that you've made on your own. I know you've done that on your own, right? That thing you've noticed in your backyard looking up at the sky, that is harder to explain in the context of this model. So is that going to convince me now that the Earth is moving around the sun? Maybe. Right? Yeah? I think I could explain the seasons with this model. So the Earth, this orbit that the sun takes around the Earth changes a little bit over the course of every 365 days. and just such enough that sometimes it rises high in the sky and sometimes it's low in the sky. So in the summertime, it's still going around us, it's just a little bit higher in the sky. In the wintertime, it's a little bit lower in the sky, but it's still going around us. Yeah?
Is the constellations at different times of year?
Different, well, the stars are going around us too. So the point of this exercise is just to sort of play around with how do you address these things, right? So we have this idea that, I mean, I think some people look at this and think, well, this is ludicrous. This is ridiculous, that the Earth would be immovable and sitting still and things going around us. The point I'm trying to make is this is actually probably the most natural thing you could think of. I mean, it looks like stuff is coming up and going over us. It doesn't feel like we're moving or spinning, right? It doesn't feel that way. And in fact, if you try to rule it out, it's not so easy. It's not so easy. So the context of this lecture then is to talk about how we began to look at the universe and build physical models like this at all, and then to test them and to try to see whether this is right or whether this is wrong, and why it took so long, in fact, for really smart people to figure out that this wasn't right. Okay. So thousands and thousands of years ago, as far as we can tell, most ancient people believed that the universe looked something like this snow globe. And this is a natural thing, right? This is what it looks like. If you go outside on a really clear day and you look around, the sky is arched, the ground looks flat, and you could very much imagine yourself living like this, right? Especially if you lived in a tent, which was basically a dome over your head. You know, it's very natural to think of sort of an extension to that home that you live in as being sort of the same kind of thing. There are some cultures that even thought of the Milky Way as sort of a seam in that tent. Now, eventually, people figured out that this doesn't quite work. There are a couple things about this that don't quite work. So, for example, imagine that this room were basically this universe, okay? And so instead of the ceiling being flat, it's arched, but otherwise it's something like that, right? No matter where you are in this room, you can see any point on the ceiling, right? You can see in that corner and that corner. But it turns out that on the surface of the Earth, that's not true. That there are certain cities where you can see constellations, and then you go to another city that's far away from that city, there are constellations you can no longer see. And that's an observed fact that eventually you can piece together as long as you've traveled far enough. You have to have the resources to travel hundreds of miles to begin to notice these subtle differences. And you have to have the kind of lifestyle where you can actually spend time looking up at the stars and thinking about these things. But if you think hard enough about it, you can begin to show that this model doesn't work in detail. So what made people begin to change their minds and to begin to ask questions about pictures like this? As far as we can tell, I mean, it's hard to know, right? Because it could be that there were sort of radical thinkers living thousands and thousands of years ago that realized that this kind of picture wouldn't work. It's hard to believe there weren't some people who were doing that. But any record of that has been lost. But we do have records of something that very special that seemed to have happened in this part of the world around the year 600 BCE. So specifically, there are a set of Greek colonies, Ionian Greek colonies that were founded by Greek-speaking people off the coast of Turkey here. And for whatever reason, people in these independent city-states began to think about the world in a radically different way than people had thought about it before. Specifically, there was this city called Miletus that was a wealthy Ionian port city. And so this was sort of a center of trade, and these Ionian Greeks were all about sailing, right? So they would sail, or they had ships that they would travel all over the region, trading, exchanging ideas. They had a kind of sort of way of looking at the world that they were very accepting of new ideas. And they were also fiercely independent people. And they questioned authority, and they were sort of about self-sufficiency. That was one of the things that sort of characterizes these ancient Ionians. In particular, there was a guy named Thales living around this time, and he is widely regarded as the first sort of proto-scientist that we have record of. Thales is a pretty remarkable person. So again, living around the year 600 BCE. He was, for example, the first person to divide the year into 4 seasons. He was the first person to basically figure out there are 4 seasons, and then in fact the day could be divided into 365, and the year could be divided into 365 days. He's said to have predicted a solar eclipse in the year 585 BC. He did lots and lots of things, so I won't go into everything that he's known for, but basically he's responsible for 5 fundamental proofs in geometry. He turned out to be extremely wealthy. He was a great business person. He was supposed to be a great engineer. And he had lots and lots of students. He founded a school of thought, and students flocked to him to learn from him. One of his students is known as Pythagoras. Okay, so if you've heard of the Pythagorean theorem, Pythagoras' theorem, Pythagoras was his student. So, but among all of the sort of amazing things this person accomplished, the thing that he's probably most known for, and probably the most important and most radical idea that he had, was that you could explain phenomenon in the world, so phenomena in the world, could be understood in material terms. So everything you saw around you, from why the earth exists, why tides come in and out, why people get sick, all that stuff be explained by physical things without appealing to spirits from beyond the physical world. This was a radical, radical idea. So Thales and his students sort of sought to explain things. That was kind of their whole deal. They'd be like, there's lightning. Why is there lightning? And they'd come up with theories for why the lightning happened. That did not involve Zeus throwing lightning bolts. So for example, they noticed that every now and then there was an earthquake. And they suggested that earthquakes are caused by waves crashing into the earth, not by gods having a fight. They believed that the world originated from water via natural processes, and it wasn't created by the gods, but it was actually born of some physical process. Now, the important thing here is not that they had this theory for earthquakes, which is totally wrong and ridiculous, we now know. That's the point, right? The point is that you can prove it wrong. So they had a theory that the earthquakes are caused by waves crashing into the earth. Now eventually you're going to be able to disprove that, because sometime there's going to be an earthquake and there's no wave. So you can disprove that idea. That's important, because if your idea for what's causing earthquakes is that Zeus got mad and kicked something, that's going to be hard to disprove. So these Ionian philosophers basically rejected traditional mythological explanations for everything. They said, well, let's come up with some more physical reason why. So, for example, Anaximander, who's probably Thales' best student, he suggested that thunder came from the shock of clouds ramming into each other. Again, we now know that's not true, but it was an interesting idea. He also proposed that animals, including humans, had evolved from simpler forms. Okay, now this is a view that Charles Darwin would later sort of back up with evidence 2,000 years later and explain a mechanism that made sense. But this is a pretty remarkable thing if you think about it. So more than 2,000 years ago, people were already thinking of the idea that humans and all animals arose from simpler forms. The point here is that all of these ideas are physical ideas, and therefore they could be falsified. They make hypotheses, and these hypotheses in principle can be falsified. And that fundamentally is what science is. Science is about ruling stuff out. Okay? It's not about proving that things are absolutely true. It's about proving that things are wrong. So let me just roll a few other things. So that these people who were living back then they had really interesting ideas. So Empedocles is another sort of important figure from this time, living a little later, 450 BC. He is the person who's responsible for this fundamental idea that there are 4 elements. The idea that there are elements, the word elements basically comes from Empedocles. But in his picture, there are 4: air, earth, fire, and water. And everything you saw was some admixture of these 4 fundamental elements. This idea lasted a very long time, by the way. Another thing that he did is he argued that air existed as some finite, something, that it was made of a substance. So he said, look, even though you can't see it, there's something there in the air. And I actually have I brought a really complicated demonstration to show you how he made this argument. So the story goes, and by the way, a lot of this stuff, we don't have direct written records from these philosophers. We have sort of secondhand accounts. So a lot of what we know about these people is stuff that Aristotle wrote. So Aristotle said, Empedocles said this. I think he's wrong because of this reason. So we have these sort of secondary sources. But anyway, there's this idea that Empedocles made the following argument to prove that air existed, that there was something there, right? So there's this thing called a water thief that people in these Ionian cities used. And it didn't look like a straw, but the basic idea was like a straw. And at the end of it, there was a bulb that had some holes in it. And you would stick this bulb into water. It would fill up with water. Then you could put your thumb on the end and pull it back out of the water, and then let go, and water would come out. Right? So it's the same thing as a straw. I'm sure you've done this. You put your finger in the straw, and then you let it out. Right? You catch water. You can play this game. Okay, we've all played this game. I play it for hours most nights. But he said, look, okay, that's interesting. Well, what's keeping the water in there, for one? Why does the water stay in there when you do this? And more importantly, if you mess up the game and you put your thumb on the straw and you stick it in the water and you never let your thumb off and then you pull it out, there's no water in the straw. Right? You've done that too, I assume. Right? So why is that? Well, he said, look, that's because there's air in the straw. There's stuff in there. So when you don't let it come out by putting your finger on the end of it and then you stick it into the water can't get in because there's stuff in there that's keeping the water out. Therefore, air is made of something. It's not nothing. So there can be things that exist that you can't see. This is a pretty simple line of reasoning, right? But it's pretty profound. So there's more than meets the eye. He sort of proved that by thinking hard about something, you can argue the existence of things you wouldn't otherwise know. Maybe my favorite philosopher from this time is this guy named Democritus of Abdera. He was called the laughing philosopher because he had this philosophy that, if you were happy, it was better. he had a lot of interesting ideas, but one of the ideas that he had, that by the way, people like Aristotle flatly, did not follow, thought this was ridiculous. But he proposed that there were many worlds that exist throughout the cosmos, beyond the Earth. And by the way, that's something that we now know is true. And we know that there are many, many worlds that exist beyond our solar system, all throughout our galaxy. But we've only known it really with some certainty in the last 20 years. The other thing that Democritus said was that some of those worlds are populated with life. So that there are living worlds beyond the sun that exist throughout the cosmos. Now that's something we actually don't know. We don't have any evidence that that's true. But it's something that astronomers are hoping to verify directly sometime in the next 20 years. He also believed that everything was made of some individual unit that he called an atom that could not be broken up into smaller things. And he believed this was true for everything. Humans, human hearts, human brains, and even the human soul was made of some physical thing called an atom. And of course, the word atom that we use today comes from this. The modern idea of what an atom is of course different in detail than his idea of the atom. But this is still pretty amazing for someone who was living this long ago. The upshot of this is that, of these so-called pre-Socratic philosophers, is that people living more than 2,000 years ago were not lacking in ideas. In fact, they were really smart. Okay? They thought hard. They had really good ideas. Some of their ideas were wrong. They disagreed with each other, right? They weren't infallible, but they were smart. The thing that they lacked was the technology, and at some level the hardcore scientific method that we have today to test these ideas. They had lots and lots of ideas, but they didn't have really good ways of winnowing them down to the ones that worked and the ones that didn't work. They didn't have a good enough technology to test a lot of these ideas. And that wasn't really the way a lot of them thought about the world. They were more about philosophical arguments than they were about actually performing experiments. And that's one reason why people argue whether or not these people were really sort of scientists in the modern sense or proto-scientists. But regardless of what you call them, they made really a profound impact. Let's flash forward into probably the seminal figure of ancient Greek philosophy, Aristotle. So Aristotle was living sometime around 350 BC. I think it's hard to argue that he was not the most influential thinker of antiquity. He was Plato's student. He made an important impact on biology, philosophy, mathematics, and astronomy, and lots of other things. And he had theories about all kinds of stuff, and he wrote about them in great detail, and he was just wrong about everything, pretty much, turns out. But at some level, maybe that doesn't matter, because the point was to have a theory and to write it down. But he was very, very smart, and his ideas, he was such a convincing writer. His rhetoric was so powerful that his ideas lasted a really long time. He was the authority of basically all of this stuff well into the Middle Ages. For our discussion, the most important thing is he developed a very specific and well-reasoned cosmological model. And what underpinned his cosmological model was that the Earth was a sphere. So we spent a lot of time talking about this. But he made very concrete arguments about why he thought the Earth was a sphere. So I've mentioned these already, but just to go into them a little bit more detail, he said, look, there are stars that you can see in some towns, but you can't see in others. Okay, so imagine you're living in some place on Earth, and here you are. But there's a constellation down here that exists. You can't see it. The reason why you can't see it is this is your horizon, and you can't see things below the horizon. Okay? because the curved Earth blocks your view. What he said is that, however, if you travel to another city, let's say far to the north of where you are now, then suddenly you could see constellations that you could never see before. And his argument was this happens because the Earth is curved. And so as you walk over the curved Earth, you're suddenly revealing new parts of the sky that you couldn't otherwise see. Does that make sense? Are there questions about this? Another thing we've already heard about is that during a lunar eclipse, the shadow that the Earth casts is always round. And it's hard to always cast a round shadow unless you're a sphere. Keep in mind that this means that they understood what a lunar eclipse was. I've talked about this before. They had a good sense. They understood what was going on during a lunar eclipse. They knew that the Earth was casting a shadow on the moon. And finally, this thing about ships and horizons. If you look out and you see a ship sailing away at the horizon, the first thing that disappears is the hull, and the last thing that disappears is the tip of the sail. So with these three very concrete and specific arguments, he said, look, any reasonable person would then say, the Earth cannot be flat, it's curved, and moreover, I love spheres because I'm a student of Plato, and we love geometry and blah, blah, blah. Spheres are perfect. Turns out he thought spheres were the perfect shape, and therefore it makes sense that the Earth would be a sphere. So there were sort of arguments and then sort of philosophical prejudice about why spheres were sort of the natural shape. And he put all this stuff together and said, it therefore makes sense that the Earth is a sphere. Now, this is a crazy idea, that the Earth is a sphere. All right? I know to you, you're like, what are you talking about? It's not a crazy idea. Imagine you had been told all your life, and you grew up believing that the Earth was flat, because that's sure what it seems like. Now, right, there's some philosopher who tells you, no, the Earth is a sphere because shadows and moons and stuff like that. Right? How is this possible? So you're saying we're like ants living on a ball? But if you're ants living on a ball, if you're at the bottom of the ball, you fall off. But that's not true on the Earth. It doesn't matter where you are on the Earth. You don't want to slide in one way or the other. You stay down. Why? What's going on? Aristotle said, I got you covered. Don't worry about it. I got this all figured out. How does he make this sense? How does he make sense of this? All right. Here's his answer. The Earth and all earthly materials, including us, are endowed with a tendency to fall towards the center of the universe. Okay? That's just what they do. And therefore, the Earth is at the center of the universe, because otherwise it would fall towards the center of the universe again. If you displace it from the center, it'll just come right back. And we all want to fall towards the center of the universe. That's why we always want to fall down. The heavens, though, are made of different stuff. They're not made of stuff like us. They're made of perfect stuff. And that stuff does not want to fall towards the center of the universe. So the stars, the planets, the sun, sort of the moon is a special case, sort of, are made of an unearthly perfect material called ether. And that ether is uncorruptible and perfect. And all that stuff here on Earth is the kind of thing that tends to decay, and it's kind of gross, and it's subject to sort of bad things. That's us in the middle. So the heavens are up there incorruptible, and we are this corrupt stuff that's found its way down to the dregs, down at the bottom. Well, this is very different, by the way, than the way most people think about the Earth-centered universe. This is what he thought. This was really the message. The Earth is fixed. It does not move or spin. The stars and the moon and the planets all orbit around us. So again, the Earth is corrupt and subject to decay, and the heavens are perfect and incorruptible. All those objects up in the heavens are perfect. They're perfect spheres. They have no blemishes, unlike the Earth, which things are dying and there are wars and, it's bad down here. This is his model. During the Middle Ages, Aristotle was the standard scientific authority throughout most of the world. Arabia, Persia, Central Asia, all throughout Europe, Aristotle was the voice that everybody studied and everybody understood. Literate people throughout the world believed in Aristotle's view that the Earth was round, by the way. There was no surprise that Columbus assumed the Earth was round. That was not a radical notion. Anybody who could read thought the Earth was round. If you read Dante, which is way before 1492, it's built in there. You can read it. It's clear they're assuming the Earth is round. The thing that Columbus got wrong is that he didn't know how big the Earth was. He thought the Earth was a lot smaller than it really is. Right? So he thought he had hit India. Had there been no North American continent, no one would know the name of Columbus, because he would have just died in the ocean. Right? Now, so this is the model, Earth in the middle. A few years after Aristotle died, this young person named Aristarchus lived in the island of Samos, came up with a crazier idea, an even crazier idea than this, that the Earth was round. He said, yeah, the Earth is round, but we're not in the middle. He suggested that the sun was the center. And I'll talk about this later, but how did he do this about 250 BC? He suggested that the sun was the middle. The sun was in the middle and the Earth went around the sun. What was his reasoning for this? Well, it turned out he figured out how to figure out how big the sun was compared to the Earth. And I'll talk about that in another lecture. But basically, he figured out the sun was way bigger than the Earth. And he just said to himself, well, it doesn't make any sense for the big thing to go around the little thing. The little thing ought to go around the big thing. So I think the Earth goes around the sun. Now, Aristotle had already argued that this could not happen, and I'll tell you why. But his ideas lost out, People were like, this young upstart Aristarchus, he's crazy, he's saying that Aristotle's wrong, obviously that's nuts, so we're going to dismiss this idea. Copernicus, who's well known for proposing this idea much, much later, referenced Aristarchus in his notes where he presented the heliocentric theory. So he was aware of this during the Renaissance in Europe. So why did Aristotle dismiss this possibility out of hand? So why did most sort of philosophers at this time think that the Earth could not possibly be moving around the sun? It wasn't really out of some prejudice, actually. They had thought about it and said, look, there's no evidence that this is happening. What's the evidence? So Aristotle said this. He said, look, if we're moving around and there are all these stars out there, we should be able to see it. Right? If you're walking through the forest, you know you're walking through the forest. Because there's you see different trees move with respect to each other. Right? Sometimes you see a tree, then you walk a little bit, and then its line of sight with another tree shifts. So if I'm walking in front of you, I can tell I'm walking because the positions of your heads are all shifting around. Right? I can look and see it. And that effect, the things move, as you move, your view of other objects change, is called parallax. And you're very familiar with this idea of parallax because video game designers use it all the time to trick you. So look at this. Which pyramids are in front and which are behind? This is a two-dimensional thing, right? Which ones are in front?
In real life or in this?
Well, in this, they're all at the same distance because this is in 2 dimensions. But which ones look like? Yeah, the big ones. But look at these in here, right? Look how fast this thing's moving compared to the tip of this one. See how it passes it? You know, your brain isn't consciously doing that because your brain sort of subconsciously does this for you. You don't even have to think about it. The things that move the most are in the front, and the things that move the least are farther away. But the point is, if you're in sort of this sea of stars, imagine there's a star on each point of the pyramid. They would all be shifting back and forth as the Earth moved around the sun. Does that make sense? This is what Aristotle said. He didn't have a video game, but he thought about it. Okay? He said, you don't see this. So if Aristarchus is right, and we're going around the sun, I ought to be able to look at the stars at one time of year, and look at the stars at another time of year, and they will have moved a little bit with respect to each other. That does not happen. The stars are fixed. They're in a lockstep relative to each other, always the same. You never see a difference. People understand the argument? So let me just explain to you what I'm talking about. This is a view of the night sky, and all that happens is the stars come up and go down. But the relative positions of those stars stay that way, and they always stay that way. Night after night, those two stars are always this far apart. They just move together in the sky. How does this break? Look at the moon here. The moon's not moving. You know how it looks like the moon's following you when you're in a car? That's because it's really far away. So when things are really, really, really far away, there's no parallax. So the moon is so far away here that it just looks like it's sitting there, right? So the only way for the stars to look like they're not moving with respect to each other is that they're so far away that the distance we move over the course of a year is nothing compared to how far away they are. Does that make sense? So Aristotle dismissed this possibility out of hand because this would have implied that the universe was so ridiculously big it doesn't make any sense. So what Aristarchus was saying was like, no, that is possible. Maybe just stars are just really, 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 really far away and we can't see them move. And that turns out to be the case. The stars are so far away, in fact, that if you took the distance between the Earth and the Sun, which is basically how far we move in the course of a year, and you shrunk that down to the size of a nickel, the nearest star would be 6 miles away. So in order to see that parallax shift, you would have to measure with your naked eye. You'd have to be able to basically see a nickel from 6 miles away and see how big it was with respect to other stuff, which is impossible. You can't do that with your eye. So the reason why the ancient Greeks never saw this effect is because it was unobservable with the tools they had, and the tools they had were their eyes. Today we measure this regularly, but it's because we have really sophisticated telescopes. Okay. The next big player in the history of astronomy is a guy named Claudius Ptolemy. He lived around 100 AD. He was Greek. He wrote in Greek, but he lived in Alexandria, Egypt, which was controlled by Rome. Okay? This was a Roman city at the time, and he was a Roman citizen. And he wrote lots of influential things, but one of the things he wrote that was particularly important was something on astronomy that became known as the Algemest. It had lasting importance in Islamic and European science. And basically what he did is he had compiled all of these astronomical tables of what stuff looked like in the sky for about the last 800 years. So when we went back, it turns out the ancient Babylonians kept really precise records of where the stars were at night in the sky and where the planets were. He compiled all those records, added them to his own records, and then developed models to explain where the planets would be in the sky and the stars would be in the sky and eclipses and all that kind of stuff. Why did he do this? Well, one of the things he did is he was an astrologer, and so he wanted to be able to predict all this stuff so he could predict the future. That was one reason. He was also a mathematician and just wanted to do this the right way. So he had all this great data from the Babylonians, et cetera, and what he realized, looking hard at all these data, was that this picture that Aristotle had presented does not work. And what he had to do was he had to build a more complicated model that began to look like this, and I'll talk about it briefly, to explain everything we see in the night sky. So this simple model that was kind of pretty, turns out doesn't work. There's a lot of stuff that if you look at the sky in detail, it just doesn't explain. So what he attempted to do is add a bunch of bells and whistles to it to make it work. So one of the things it predicted, Aristotle said, is everything's going around in circles that just keep moving constantly in circles. But it turns out that if you pay very close attention to what the planets are doing in the sky, this doesn't always happen. This is your retrograde motion. So every couple years, if you look at the track of Mars in the sky relative to the fixed stars, it does a zigzag. So this is a series of images taken in 2005, 2006, and every couple of weeks they took a picture of Mars and then lined it up with respect to the background stars. So normally what Mars does is it just moves along like this with respect to the background stars. But every couple of years it goes like that and then stops and does a zigzag and come back. That does not work in Aristotle's model, because he would have said, look, Mars just keeps going around us. He doesn't say it does a zigzag and come back. So what Ptolemy did is he fixed Aristotle's model by introducing something called an epicycle. So he said, look, it's still going around the Earth, but the center of the circle going around the Earth, there's another circle that loops, and it kind of does a loop-de-loop. And if I add my loop-de-loop in, if I add this epicycle, I can start explaining things. You might look at this and say, boy, that's crazy. But so ingrained in them was the idea that the Earth was not moving that this is what Ptolemy did. And it turns out this model did a really good job. And he could predict all kinds of stuff. There's even other things he had to do. It turns out that the planets don't always move at the same speed. They change speed throughout the year. So in order to fix this, he had to have things not orbit the Earth, but orbit something in between the Earth and something else. So it became really complicated. So he basically, with a lot of effort, developed this complicated model. And by the way, what's really going on is that the Earth is going around and Mars is going around, and every now and then the Earth overtakes Mars, like you would overtake a runner in an outside track. So if I'm coming up on somebody in the outside track, I look forward at them, and then when I pass them, I look back. So it looks like they were going forward and then going back. So that's what this does. So that's perfectly well explained in the context of how we understand the solar system now. But this idea would have been way, way too radical for Ptolemy at the time. So he introduced this other thing. So Ptolemy's picture of the universe, basically his cosmology, with all of these loop-de-loops and stuff like that, this kind of what looks to us now, I think, with modern eyes, is sort of ridiculous. This was the accepted model of the universe, of cosmology, for 1,300 years. It's the longest lasting, single most successful model ever hypothesized, and it lasts longer than any other known model that we know of. And eventually it crumbled in the face of new data in Europe 1,300 or 1,400 years later. And as I'll talk about next time, over the next 1,000 years or so, these ideas of Aristotle and Ptolemy, they would basically be pushed and confronted in their most sophisticated ways in Arabia, Persia, and Central Asia. That sort of was the center of the intellectual world, shifted over there and into India during that time. And these people, like Alhazen and others, realized that Ptolemy's model wasn't even self-consistent. And you had to add even more bells and whistles to make it work. And so this began to make it crumble, and they were the first people to suggest, reintroduce this idea that maybe the Earth is moving. and we'll finish up with that on Friday. Thanks.